still find it useful to have them explicitly. And yeah, almost no mathematical rigor. Right, so let's see. Let's start. So this is the part I think I can really rush through it because I'm certain you have seen that at many levels. I just want to go through a recap of all the symmetry operations that we are talking about when we are talking with molecular or crystal symmetry. Apparently, it has become a habit to propose the symmetry operations as a choreography here on the stage. This so I was told by the organizer, so let's go. So the first is rotations, which usually note n or Cn. So typically C2 would be rotation by 180 degrees, so this one is kind of okay, we can still do it. C4 is a quarter of a turn, okay, and C43 would be 3/4 of a turn, so that in here, yeah, okay. So it's a question. It's useless to go beyond one turn because it's equivalent, right? Mirror planes, which we usually note M or sigma. So here, so I have made a mirror plane, but you don't see that because I'm essentially invariant with respect to this mirror plane, more or less, right? I won't do the other planes, I'm sorry. Inversion center, noted -1, or I like inversion. I will do on the beach this afternoon. Just as a side note, so if you have inversion for a molecule, it's always at the origin. I think this is pretty obvious when you think about it. And either you have one or you don't have any, but it's not like you can have several of them. Fair enough? Good. Rotor inversion or improper rotation. So this one, usually I find it useful to have a short reminder of that one. So it's a combination of a rotation plus an inversion, which also I will have to do on the beach later, and probably with some help and some people spotting. So you write them n, or -n, sorry, or Sn. And the thing is, it's really a symmetry operation in itself, because it may leave a molecular invariance, even if the rotation alone or the inversion alone doesn't. So typical, very simple example for that is this molecule. So typically when I ask the students what's the highest rotation on this molecule, they tend to say C3, so rotation by 120 degree, because this is the obvious thing that you see. But in fact, it's -6. So -6 again means rotation by 2 pi over 6 would bring this atom here, plus inversion atom there. So this molecule is invariant by -6. And yet, there is no 6 for rotation, and there is also no inversion. Okay? But if you get that wrong, you simply cannot identify the proper symmetry of the molecule, and this is the very start of your reasoning anyway. So this was for molecules. For crystals, so if you move to crystals, you need to add a couple of things. You need to add translations by lattice vectors, so those are symmetry operations as well. And then you have combination of all those point symmetry operation we've seen with partial translation. That would be the screw axis and the glide planes. Yeah, maybe the screw axis, I think I can do it, so something like that. So it would be translation plus, yeah, okay. So that would be translation downwards plus a C2 rotation, yeah? Something like this. Glide plane is a bit more complicated. So this is for crystal. If in addition to that you want to take into account magnetism, so this is the only slide about magnetism. I'm not going into detail at all because there's already enough to chew. But let me just mention this. So you want to add one extra symmetry operation that usually it's called the time inversion symmetry that you write 1 prime, and whose action is just to flip the magnetic moment up and down. So it's like the inversion for a polarization, but it reverses the magnetization. And then you may combine this with all the other symmetry operations that you have. So just as a reminder here also that I find useful, when you talk about magnetism and magnetic symmetry, you should not forget that the magnetic dipole, it's not a true vector. It's not a polar vector like polarization, right? It's, if something, it's more like an actual vector, which is best represented by this kind of loop. So if you want to intuitively think about the action of a symmetry operation on this magnetic moment, it's better to keep in mind that this loop is the object that you want to transform. And when you keep this in mind, just as a game, we can see what happens when you apply different symmetry operations to polarization or magnetization. This time inversion symmetry doesn't change anything to polarization, but it just flips magnetization. But the inversion, the spatial inversion, of course, changes polarization from up to down, but doesn't change anything to the magnetization here, because this loop doesn't change, okay? And so on, and then you can continue with this example. So again, here, warning sign is just, don't forget that not every arrow behaves like polarization. Okay, so with this, as certainly you know from your classes, we have a number of constraints. When you go to crystals, there is something that's called the crystallographic restriction theorem that says that you're not allowed to have any rotation, but just a limited number of them. So 2-fold, 3-fold, 4-fold, 6-fold. And so that all the combinations you can make from that are in a finite number. That's good news. So we have 32 crystallographic point groups. If you add magnetism to that, this raises the number to 122. We have 230 crystallographic space group, and more than 1,600 if you add magnetism, and so on. So this is all finite numbers, okay? Large to some extent, but finite. So essentially, all this has been already calculated, tabulated in any way. So the work we have to do, especially as experimentalists, is never to really rederive those things, but just navigate all the sources that we have to find our way through this maze, okay? And very quickly for molecular symmetry, so then there is no particular restriction, the rotation, so you have many more symmetries like that. You do not only have finite groups, you can have infinite number of rotations, especially when you have a linear molecule like this one. And you can have rotations that are otherwise not permitted in crystals, like in this molecule S8, which is a nice example because S8 is both the chemical formula and the symbol for the symmetry operation. Okay, yeah. Right, so this is for crystal symmetry, right? I think this is pretty good as a start. So now we can go into the group theory itself. So as I said, it's about definition. I'm sorry, I still want the text. So let me just go through it very quickly. Definition of a group, it's a mathematical structure where you have elements and you have an operation, and those need to satisfy a number of properties. The property of closure, the existence of an identity, associativity, and inverse. My question here to you is there anyone in the room who has never seen this? Yay! Okay, so let's then skip it. The main thing, of course, that makes it work is that the set of the symmetry elements that leaves a molecule invariant or a crystal forms a group, so this is the very reason for all of this. Second notion I might need later on is this notion of site symmetry, okay? And then again, it's a definition, and then it's for a particular atom A in a crystal or a molecule, it's the set of symmetry operation that leaves this particular atomic position unchanged, okay? So this is something that is also a point group. It's a subgroup of the group of your molecule or your crystal, and typically you don't, I mean, you can find it just manually by checking the symmetry operations by one, but more often it's again tabulated in the table for crystallography, and if you had never paid attention, this is where it would be here next to the Vikov position. So Vikov position, site symmetry symbol, and then the coordinates, okay? So this is fine. So now let's get to the main piece of meat there will be images later on. Okay, this is, I think, the last big text. So main big piece of meat of this presentation is the idea of a representation of a group. So let me go just a little bit mathematic first. So you need a vector space, okay? You need your group, and the representation is just a mapping where to each element of your group you're going to associate a square matrix written on your vector space, such that the structure of your group is preserved. So you're really taking your group of symmetry operation, which is an abstract object, and you're transferring it, so to speak, to a group of square matrices. This is the only thing that you're doing. So then there's a number of pieces of vocabulary that are still important. So the dimension of your matrices, and it's a square, so n by n. The dimension n is also called the dimension of the representation. Because you need a vector space and you're writing matrices, you need a basis to do so. So the basis of the representation is the basis that you're using to write the matrices. And finally, very important, the characters of the representations are the traces of the matrices. So sorry, that's a bunch of definition, but we'll see many examples. Just before we go a bit further, so here I speak of vector space as a completely abstract thing, but in practice in physics we have many such vector spaces. We have all the quantum states or wave functions. All this is linear algebra. We have all the atomic displacements for vibration. So this is what we're going to do in a bit more detail. And we have all the tensors that describe the physical properties. So in principle, that can be all of this for us. But for the moment, we can keep it completely general and use any vector space. So if I want just to make a graphical representation of that, right, I can make a table where I will just, take a point group as an example. In this particular case, MM2, orthorhombic polar. It has 4 symmetry operations, 1, 2, okay? I note here the direction with respect to some coordinate system, and to each of the symmetry operations, I associate a matrix that forms a group so that respects this condition. So that's it. So let's start with a basic example with that. That's called the totally symmetric representation. So what is that? So I will make it extremely simple, and I will just associate to every single symmetry element the number 1, or the matrix 1 by 1, if you wish. So my table would look like that. Is that a representation? Yes. I mean, it's completely trivial that this satisfied all the definition properties that I've mentioned earlier. So this is undoubtedly a representation. Also, it always exists, right? I mean, whatever group you take, whatever vector space you take, you can always do that. So now the question is it useful? Well, actually, yes. I mean, what this says, in physical terms, is that you do not change anything whatever symmetry operation you're applying to your system. So in other words, it describes how a scalar property transforms like. Okay? So if you take the temperature of a crystal and you apply a 4-fold rotation, obviously temperature doesn't change. And it doesn't change whatever symmetry operation you want to apply. Okay? So what I can say here is that all the scalar properties transform like the totally symmetric representation. So transform like here, I will use this very often because to me this is kind of key. I mean, if you're not very familiar with the topic, this is the only thing I want you to remember. It transforms like, okay? So I see, I see that Brahmi here. So transform like, okay, is the change the tip of group theory, if that makes sense. A last remark on that, right? So this totally symmetric representation, it has one property, that it's not what we would call faithful. So if I give you the matrix, you're not able to tell me which symmetry operation it corresponds to, right? But we never said that it had to, so this is perfectly fine. Sorry. Okay. So now we have a distinction to make between representations that are called reducible and representations that are called irreducible. All right. Right. So this distinction is made in the following way. So you have your matrix associated to every symmetry element. So if you're able to find a base in your vector space where all those matrices can be written in the same block diagonal form, like this, then the representation is called reducible. And if you can't do that, it's irreducible. Okay, fair enough. So in my case, I had some matrix of dimension, I don't know, 4, 5, 6, and I can decompose it into this block diagonal form just by a change of coordinate system in your vector space. Okay. So in practical terms, if the representation is irreducible, you call it an irrep, just because irreducible representation is a bit long. And if not, it's just a rep. So once you've done that, what you can do is to reduce or decompose this original representation, okay, that was reducible clearly, into a sum of irreducible. So what you're doing is just that you're splitting this into 3. Up. Yep. So you're just splitting this into 3, you keep only the blocks and you consider them separately, okay? So mathematically what you're doing here is that you're separating your vector space into subspaces that are stable by each of the symmetry operations. But never mind, visually this is what it would look like, right? So I have separated my original matrix and my original representation into 3 lines. And I can say that this is representation A, this is representation B, and this is representation C. Okay. So what I can say is that my original representation here is just the sum. So in mathematical terms, this symbol here would stand for the direct sum, as for vector spaces. But very often people in papers are lazy and they just use just a standard plus sign, okay? And when you have that, it's quite obvious to see that the dimension that I had originally is just the sum of the individual dimensions, and also the characters are the sum of the individual characters, okay? Okay, so this is this very important part of reducing a reducible representation. So now there's a bunch of theorems working on that, and this is where we can't really afford to get too mathematical, so I would call them the everything works nicely for us theorems, okay? I just put the names here if you want to look it up, but you will find them in any of the sources that I indicated at the beginning. There is Maschke's theorem, Schur's lemma, and especially this one, the wonderful orthogonality theorem. So wonderful is not from me, this is really how people call it. So you will find it under that name because it happens to be extremely useful. So this would be for the hard mathematical part. This is now my formulation, layman, experimentalist, ignorant formulation of what this means, okay? And I would say it in such a way. So an IREP, so irreducible representation, it's a basic building block to describe how something may transform in a well-defined way under all the symmetry operations of your crystal. We'll see examples later, and especially concerning this well-defined way, which you might find a bit puzzling. Second thing, the IREPs that we need for the point groups and the space groups, this is all done and known and tabulated. So again, it's all about finding your way in this literature, and you usually don't have to redo all those things. Then every representation for any kind of phenomenon that you might want to study can be decomposed into a sum of IREPs, and this decomposition is unique. So you're really using the IREPs as a base, in a way, to describe any kind of thing that you want. And finally, all you need is love and the character tables, but also love, but also the character tables. Okay. So having said this, the question is where to find them. The answer is everywhere. Okay, so you will find this on the web. There is endless sites giving you those character tables for crystal point groups. If I just want to go back to this Bilbao crystallographic server, funnily enough, they are a bit hidden. You can go on the website and they would be here, so point group tables, okay? And all the tables that you will see in the following I took from this site. But starting with this one, so this is what the character tables really looks like, okay? So I take again the same point group, which is this polar orthorhombic MM2, and this is how the crystallographic server gives it to you. So you have first the point group symbol, I'll come back on that, then the list of symmetry operation, just like I did before, and then you have one line per IREP, okay, with a symbol, I'll explain this also a bit later, and with the character, okay, so this is why it's called a character table. There's different notations, again I'll come back to that, and there's also always a last column that people call basis functions. For a long time when I was a student I found this formulation confusing. Usually I prefer saying it's a basis vector in the sense that this corresponds to the basis of the vector space that I've been talking since the beginning, right? But you can call them functions if you wish. So in practice you see that there are some of them that you always find, so x, y, z here. So this would be the basis to describe any kind of vector property, so that includes polarization, that includes displacements, that includes all these things. Typically you also have the second order polynomial, okay, that you might use to describe second order tensors, for example, and typically it's not very useful for us, but you also have the rotations that you may find as J or as R, or there's different notations, okay. So again, if I want to read this table in the way that I was mentioning before, I would say that a translation along Z transforms like the IREP A1, meaning, it's the totally symmetric representation, meaning that it doesn't change anything. Translation along X transforms like B1, and then I see that I have to change a sign when I applied the twofold rotation and so on. Okay, so this is the way I would read this table. So with this, let's continue with some examples, and let's wonder how polarization transforms, okay? So polarization, it's a vector, it has three components in my coordinate system, px by y, pz, And the obvious thing that I can do is that I can simply write, okay, the matrices for the symmetry operations themselves. And this is how a vector transforms by definition. So I would associate to the identity matrix, to the twofold rotation along Z, this particular matrix, and then the same for My and Mx, okay? So this is a representation. Is it reducible? Obviously, yes. I mean, it's already there in a block diagonal form, so this is clearly reproducible. So now, what if I, instead of considering the matrix of the symmetry operation itself, I'm just concentrating on the individual components of polarization. I can say that Px, so Px would be pointing this way. If I apply the twofold rotation, now it's pointing that way. If I apply this My, it stays the same, and so on. So it's quite easy to figure out how you transform each of the individual components. And instead of these pictures, you can very easily transform them into numbers, depending on whether they are the same or they are flipped. Okay. And then the only thing that you have to do in this very simple case is just to compare this to the character table that you have. You have a direct identification to the reps. So let's check, for example, Px, 1 minus 1, 1 minus 1, corresponds to, this one transforms like B1. So I say the component of the polarization along X transforms like B1. Same for, say, Pz, totally symmetric, 1 everywhere, Pz transforms like A1. And in the end, if I want to make a statement about polarization as a whole, I can say polarization transforms like this representation, which is a sum of B1 plus B2 plus A1. That would be the way to phrase it, okay? Okay, so this case is obviously very easy because everything is one-dimensional, the symmetry is low. So let's take another example from a symmetry that's a bit higher, and I will choose here 4mm, which is the point group of lead titanate, or barium titanate, for example, okay? So we have the same polarization with all my components. And then you see that it's getting a bit more tricky, because if I take Px, let's say, and that I apply this fourfold rotation, it is sent onto Py, right? So I cannot say that Px transforms in a well-defined way under C4, because I cannot express its image as a function of just itself. So what I have to do here is to take together Px and Py and consider them as a group, okay? And this corresponds to what you all know, that in a tetragonal point group, you have equivalence between the A and B axis, okay? And everything in this plane is degenerated. So in practice, if I want to go to the end of this exercise, I would write again the matrices for the symmetry operations. This time, they are not all in the same block diagonal form. I mean, not the simple one, right? And there is no change in a coordinate system that can bring them into this all diagonal form. So what I have to do is to be happy with having a 2x2 matrix here. And if I want now to compare to the character table, I have to remember that the character is only a trace, okay? And that you will find here is just the trace of this 2x2 matrix. So here that would be 2, minus 2, 0, 0, and 0. And then I can identify, again, just like I did before, the polarization of components, okay? And I would state that polarization transforms as E plus A1, okay? Last example, because it's important. So this is the most complicated character table that you might see, because it's the highest possible symmetry that we usually have, and it's the cubic symmetry, okay? So then you have a bunch of things. But if you concentrate again on only the translations or the vectors, they are all here. So all only here in one line. Okay, and this corresponds to the irrep that's called T1U. So polarization transforms like T1U, except that we are cubic and we are not able to separate all its different components, like in a cubic system. Right. Another thing that I will just allude to, okay, is all the relations that you have when you start considering groups and subgroups. So this, you can imagine, is super important when you're considering phase transition. It's all about symmetry lowering, right? So you have all these relations going on between those two, and all of them, they have their own irreps, okay? And you can just infer that there are also relations between the irreps of a supergroup and the E-reps of another group. So there are ways to go from one to the other by, say, processes that people usually call subduction here, because you're going from super to subgroup, and induction here, because you're increasing the symmetry. I see, for the sake of time, I'll not go into that, and I will skip to the last part. So is there already at this point any question before I go to the next? Yes? For the E-reps? Mm-hmm. So I'm not sure I understand exactly what you're looking for. So let me just then still go to this example and show how naturally you can go from the E-reps of a supergroup to the E-reps of a subgroup. So let's take here again the character table for C2V or MM2, okay? And I'm considering as a subgroup just the M, okay? So just identity and one mirror plane, which I take as MX. So here I have an E-rep that associates a matrix to all symmetry operations, and here I just have a subset of the symmetry operations. So, you know, it's not, you already have the E-reps, or you already have representations of M in the E-reps of MM2, okay? So,
to use this, just suppress some columns and we have the second phase. They are the same.
Okay, so this goes a bit beyond that. So in some cases, yes, but only for some physical properties and anything. So I suggest maybe we go to the end and we take again this question after we've seen all the rest, because the last part is about all these phase transitions. So this part here is really about the notations and the conventions. So this is something that no one is supposed to know by heart, okay? So I just put them here on the slides so that you have them. You have seen them once. Again, there's plenty of sources on the internet where you will find this kind of explanation, so there is nothing super exotic. I just want to make a couple of points on how to handle those different notations. So first thing, for point groups, there's mostly two types of notations that people are using, the one that's called Schoenflies and the one that's called Hermann-Mauguin. So the Schoenflies notation is this one here, and it's typically a letter with some indices, right? And historically, so it works for point group, it works for molecules, so it's more the notation for spectroscopists and for chemists, typically, okay? Physicists tend to prefer the Hermann-Mauguin because it can be expanded also to space groups, so it's much more general. Also, it's more informative about the symmetry elements that you have in there. And again, you will find the equivalence between those notations a bit everywhere. So nothing special here. For your information, there is also a meaning behind the Schoenflies symbol, like C stands for rotation, D stands for improper rotation, so on. So you have some meaning in there and some information, right? But again, no one is expected usually to know this by heart or to learn this by heart. It just comes with, you know, practice if you're really into it. So again, this is just the explanation in case you want it. I'm not going into the details. So for space group, there is not so much to say because I think the situation is much more clear, right? So everyone more or less, at least in our community, everyone uses standard symbols that you can find in the international tables, and that follows the Hermann-Mauguin notation. For information, you also have something like a Schoenflies symbol that you will find in some older papers, but it tends to be deprecated. I'm talking about the notation, not the researchers, although... who uses that notation seriously, but information, anyway. So, not so much to say here. For representation, this is where it becomes a bit more tricky. So typically you will find two notations, and here really they are equally used depending on who you're talking to. So the Mulliken symbol in the first one, it's the one that we've been using so far, right? And that goes with the letters A, B, or N, T, and F, plus some index. And the other one, there's several flavors of it, right? But it essentially goes with a letter that in that case would be gamma or some other letter plus some index. So this one, it's suitable for molecular vibrations, lattice vibration, but everything has to be at the gamma point, so zone center. So it's very nice as long as you don't move in the Brillouin zone, but if you stay, if you want to move away from the gamma point, then you have to go for something else. And this is the reason for all those notations, which definitely you need anytime you're considering anything that goes beyond gamma. So that was the case for Eric at the beginning and in many other cases, okay? So sadly enough, I mean, now the Bilbao server gives you the two notations, right? So you can find equivalents, but to be honest, there are not so many sources giving you this kind of correspondence table. I struggled quite a lot, so this is from this Bible, Bradley and Cracknell. Again, the symbols in the Millikan symbols, like those letters, they have a meaning. So again, don't try to learn this by heart. If you manipulate them, it will come out of habit. Just know that there is some information into those symbols, okay? For the space group and the other notation, so here I have to make a point. So everything that I have mentioned so far was really only about the EREPs of point groups, right? All those character tables, all those things, this is point groups. I'm not going at all into the EREPs of space group as such, because there's a lot more mathematics, because I have no time, and because I don't understand anything about it. But the main thing that I want to point is, first thing, we have an infinite number of symmetry operations, an infinite number of EREPs in general. So here we are more talking about classification of all those EREPs, okay? And they are always labeled by a k-vector in the Brillouin zone, right? And very often, there are special names or special letters that are used for special points in the Brillouin zone. Okay, so we'll have examples of that. And this, again, has been tabulated. So if you go on Bilbao crystallographic server, you go there to this KVEC, and you will find this. So as a typical example, this is what we need for everything that Eric is telling us usually. So that would be the type of symbols for the cubic, primitive cubic perovskite, with a gamma point at the center of the Brillouin zone, and then some special points, and typically M, X, and R, okay? And this is, I still went to check into the Bradley and Cracknell to check that it was the same. Fortunately, here it's fine, okay? So here comes really the warning when you go into those notations. So there's a bunch of ambiguities. The first is that in the second cluster, or PSW, never remember what it stands for, there's always different flavors for it, right? So it's not because you see that it's necessarily cluster. It can be also this other notation that goes a bit differently. So instead of having a 5, you have a 2, 5 here, and so on, okay? And even within one notation, sometimes there are ambiguities on the way to order the EREPs, right? So typically the 4 and 5 can be swapped depending on the author. And since people rarely say where they take their reference from, sometimes it's really confusing, okay? So this I took here from the Yuan Cardona famous textbook on semiconductors, right? So they give just an example of that, and they even advise to really check this notation. So this is one thing. So again, I mean, here the warning sign is just, if you see some inconsistency in the literature, you see a paper that says R4 and the other paper that says R5, you're not mad. Well, maybe you are, but it doesn't prove it, okay? So maybe it's just that the authors are using different notations for that. So always double, triple, quadruple check all those things. The other warning sign here is this, there's, in some cases, some arbitrariness in the way that you choose your coordinate system or in the setting of your space group, and this results in different symbols for the EREPs as well. So let me take the example here of the square, okay? So let's assume I want to study this square, and I have a coordinate system. So I can imagine putting the square in this orientation, right, or in this orientation. I mean, it's completely equivalent from the point of view of physics, right? There's no change, and there is no reason to say that this axis in principle and this one is secondary or the other way. This is really a matter of choice. So depending on which convention you choose, you will swap the indice 1 or 2 in this particular case, for example. So again, this can cause a lot of confusion in the literature. Same thing goes for this orthorhombic group MM2, right? So here, it's kind of always the case that the principal rotation axis is along Z, so there is no ambiguity on that, but then how do you choose X and Y? This is completely up to you, okay? So, and here again, if you swap X and Y, you're gonna swap the indices 1 or 2 of the B EREPs, right? So again, these symbols in principle only make sense if you're really accurate on your coordinate system. Otherwise, there is some ambiguity. So again, if you see some inconsistencies, and if you cannot, say, reproduce a result that you see in the literature, check if there is this kind of problem. And the second very famous case, so in some space groups, right, you have different possible settings, or you have different possible choices of origin, and those also result in different symbols for the irreps. So there is a very famous case that I think many of you have already seen in the orthorhombic perovskites, like the very classical one, the calcium titanate, the orthoferrites, the manganites, where we have the space group number 62, okay? And there's typically two settings that people might want to use: the PNMA settings, that is preferred because it's the standard one in the tables for crystallography, and the PBNM that people like very much because then you have the long axis along Z. And that's it. And you really, I think it must be 50-50 in the literature on who uses what. So again, the consequence on that, when you go into symmetry analysis, is that you're going to swap some symbols, okay? And the decompositions are going to be different. And this case is so important that you have even this paper that was published some time ago, where this lady, she needed to treat both with both conventions and really compare them to make a bit more clear, okay? So if you have a doubt in this particular case, you can go to this paper. So this is just the example of this orthorhombic perovskite for two different origins and two different sets of axes, x, y, z. Yeah. Right, so this is the end of this, say, warnings of notations. So again, not to be learned by heart, but just a couple of attention points to have every time you encounter this kind of symbols. So now let's go into the mechanical representation and what we can do with it. So the mechanical representation, my question is just why it's the representation that is generated by atomic displacements in your molecule or your crystal. So the question I have is, how do atomic displacements transform under the symmetry operation of the group? That's what I want to treat, okay? And also, how can I decompose the displacements onto a symmetry-adapted basis that I will construct with the help of the irreps? So here, for simplicity, I'm going for the water molecule because it has the advantage of being kind of low symmetry, right? It's not the most, it's not the best for us probably, but we'll have examples with perovskites also later. So for the water molecule, point group MM2, you know, there's a pattern, I've been using MM2 since the beginning. 3 atoms, so that's 3 times 3, 9 degrees of freedom. So the representation that we're talking about is 9-dimensional. So this is my mechanical representation. And I have to start somewhere. So I have to start with some basis, okay, to write those displacements. And without any prior knowledge, I can just take some coordinate axis, place my molecule in this coordinate axis, and then choose basis vector just bluntly, you know. So first basis vector will be displacements of oxygen along x. Second will be displacement of oxygen along y, and so on and so on. So that's 9 basis vector. It's in no way symmetry adapted, but this is something I can start with to write a representation. So just for the sake of making it a bit more concrete, let's do it for one symmetry operation, okay? It's this 9-by-9 matrix. So I'm considering the symmetry operation my, and I'm considering its effect on the atomic displacement. So let's take oxygen, displacement along z, that was my third basis vector, is left unchanged, okay? So I would have 3 goes to 1 here. Displacements along y is swapped, okay? So this gives me a -1 here. If I go to the hydrogen, displacements along y, so the symmetry operation first sends the hydrogen here and also swaps the displacement vector. So if you keep track of all those vectors, that gives me a -1 here, okay? And so on and so on. So this would be the matrix for, of my mechanical representation for this particular symmetry operation. So it's boring, but the good news is that we never need to do that in the end. I'm just showing it so that it can, you can have another example of representation. This is what's behind. So we have this representation in principle. What we want to do is to immediately reduce it into a sum of irreps, okay? And there's typically 2 ways to do that. So in principle, again, just to rephrase what we have to do, we want to decompose the vector space in stable subspaces. And there's 2 different approaches to do that, I would say. So one is very straightforward, but a bit black boxy. You would use you calculate the characters for your representation, you use the orthogonality theorem, and you get it immediately. And it's like 3 lines of calculation. So it's very nice, very quick, back of the envelope calculation, but it's very black box, and also you lose track of the atomic displacements that you're talking about. And the other one that we tend to prefer, especially in spectroscopy, it's called the correlation method. And this is something that's better adapted to the vibration problem or this distortion problem, I would say. So I'm not going to go at all into the first one. I'll just switch directly into the correlation method. Here I'm really just giving you the basic idea. You will have the whole thing worked out in the slides, but I'm not going through it because it would take a bit too, would take too much time, right? But I still give the basic idea, the ingredients, and then we jump to the results, okay? So basic idea is that you have a molecule, it's made of atoms, and it's pretty easy to know how the displacements of a particular atom transforms like in its side symmetry group. That's a pretty straightforward thing. This is something we can read, again, just from the character table. So the idea is to take this information and to use all those subgroup relations that we have to find out how this displacement or this irrep translates, if you wish, into the irreps of the general molecule. So you're really making this link between the side symmetry, the irreps of the side symmetry for this particular atom, and the irreps of the point group for the full crystal or the full molecule. Okay? So this is the general idea. The recipe looks like that. It looks complicated because I've really put a lot of details in there, but really it's not. And just the ingredients, what you need is just the structure of the molecule. And for a crystal, that would need a space group and the Vikov positions. That's all, okay? And then you need the character tables and those correlation tables that are also tabulated, and that's it, okay? So again, this is the ingredients, this is the principle. I will just rush through it, you can go it for yourself, and I will go directly to the final result, okay? So this is what the final results of this analysis would look like. I have my hydrogen atom, okay? Only one, because the two of them, they are symmetry equivalent, huh? The oxygen here, and I tracked, so if I displace an hydrogen along X, okay, it gives rise to A2 plus B1 here, and so on and so on. So I can really keep track of all those displacements. To formulate the full mechanical representation, I really just have to sum all of this. So this gives me, okay, this decomposition, this is a bit abstract. What I also want to do typically is to take off representations that just correspond to rigid translations, because we are not interested into that usually, and also for rigid rotations, okay? So again, we took really all the degrees of freedom, huh? So they are included in there. So in the end, we end up with this famous result that you have 3 vibration modes for the water molecule, and in terms of symmetry, they transform like A1 and transform like B2. And again, I recall the character table here, okay? So this is the typical representations now of the eigenvectors. So I just want to show you that with a bit of, say, clever guessing, you can really draw now those arrows based on this knowledge and the way that they transform. Okay? And this is in particular the case for this mode, the one with a B2 symmetry. So I can just go back into my table and I see that B2 involves oxygen displacements along Y and hydrogen displacement along Y and Z. That's all. So I can start by putting this arrow. Okay, so this I have no choice. And then I can start by putting one arrow here and just check how this is supposed to transform. So transforms like B2, I'm invariant under the identity, yeah, okay? I'm invariant under 2Z, so I can just do this twofold operation. Sorry, it's not invariant, it's -1. So I do my 2Z, and I flip the vector, and this gives me the orientation of the second vector. At this point, I still have some degree, right, because I have some arbitrariness in the way that the vectors is here, and also in its magnitude simply. But then if I keep in mind that I don't want any rigid translation, so the sum of all this has to be 0, and I also don't want rigid rotation, so the sum of the moments with respect to the center of mass has to be 0. That gives me 2 equations, essentially, that I can use to completely determine this. So the message here is that those arrows, there is nothing left to arbitrariness here. It's really completely determined by symmetry, okay? Completely. And this is not the case here. So this would be the other vibration modes that transform like A1, so totally symmetric, okay? And here I have 2. So this is invariant under all the symmetry operation and this one as well, but any linear combination of those two also works, right? So you can make as many bases as you want. So if you want to go beyond that, you need to have a couple of physical arguments to justify why the mode would look like this and not just be any linear combination of that. So this is typically where symmetry stops and some kind of calculation takes over. Well, it can be DFT, can be any kind of calculation. So does that make sense, this difference? I mean, it's kind of essential here. Here we're in a one-dimensional space, no degree of freedom at all. Here we are in a two-dimensional space, so we have some arbitrariness in choosing the eigenvectors. I will skip that for the sake of time as well. Yeah, so you go to the beach, so you will have that. So if you want to play Modoku on the beach, I give you the final result, I give you the table of characters, and you will have the solutions also at the end of the slides if you want to, if you're bored on the beach. Okay, so at this point, I think we are ready to go back to Eric, okay, and what he was telling us at the beginning about the modes and the distortions in barium titanate. So first thing is now you have the explanation for this notation here. So gamma for minus instability. So gamma means at the gamma point, okay, so it's associated to polarization or say to a macroscopic physical property. It's polar, this is reflected in the minus sign as well, and 4 is just a number that depends on the order in which you rank the ERAPs, okay? So what I want to do now, so first thing, let's plot this again. So this is the kind of dispersion curves that he was showing, not exactly the same, but exactly the same method and everything. So we had this gamma 4 minus here, there, right? And then we also had all the other modes at the different points. So first thing I want to do is to take this polar mode, right, and use the same correlation method or do the same decomposition that I was doing with the water molecule. Not going to do this in detail, I'm just telling you, you go to the crystallographic server, you go to this particular program, this is what the output would look like, okay, where you just input some very basic information on the crystal structure. He asks for the lattice parameters, that's completely irrelevant. As I said, we only need the Vikov positions and the space groups, and that's all, okay? So all this doesn't really matter, just have to be consistent with the structure that you're proposing. And then it gives you this mechanical representation. So it does the job for you, okay? And this table that you have here is another version of the table I was showing before for the water molecule. So as you can see, so what you can see typically is that this 3D, so this is the oxygen atom, contributes to one T1U mode, but also the barium and also the titanium. So there's 3 T1U polar modes, right? And all atoms contribute to it. So starting from that, again, you have this problem of arbitrariness. How do you want to define a proper base for this vector space, since all atoms contribute and any linear combination is good from the point of view of symmetry? So again, this is where symmetry stops, and this is where other types of calculation takes over. So here I want to show you one base that has been used very much in the studies of barium titanate in particular. So this is extracted from some review paper by the Czech colleagues, okay? And they even have names for that, right? The Slater mode, the last mode, and the axe mode. This is for lead titanate, but that would apply to barium titanate as well. And those constitute a base of eigenvectors that you can use to describe your soft modes. So in particular, this one with, say, that titanium vibrating against the oxygen cage. This one where titanium and oxygen goes along, but it's lead that goes against it. And this one where it's just the oxygen octahedron being, just the oxygen octahedron vibrating. Okay, so the question that we have here at this point when we think again about Eric's soft mode is, okay, so we have a soft mode, we know it has the symmetry, but which one is it, okay? And he has shown some calculations to explicitly address this question and showing that it was mostly titanium and oxygen moving, right? So the soft mode in that sense would be really that one. Also, if you remember, I had this question to him about the identity of the soft mode eigenvector and the actual distortion in the ground state structure, okay? This is what makes it non-trivial, because you might have, I don't know, from the point of view of symmetry again, you might have a ground state with a distortion like that, and a soft mode eigenvector with a distortion like this. Okay, and in that case, the soft mode theory would not really work as he meant to. So this is really this is to stress the importance of this result that he mentioned on that. Does that make sense to everyone? Okay, so again, this is just for the gamma point, so it's important. So let me just give you examples for some points at the zone boundary. So this is from another publication, again, by the Czechs. It's a random one. I could have taken anything. So here they are discussing modes at the M point, and because they are kind, they also remind you that the M point has coordinates 0.5, so 1/2, 1/2, 0. Okay? And it transforms like different representations, so again with this label and some kind of number. Anyway, so here what you're doing is you're breaking the basic lattice the invariance by the lattice vectors, you're breaking it, right? Because this displacement, the displacements of this atom is not the same as this one. So this is where you break translation symmetry, but this one and this one are identical. So this is what corresponds to this M point. Okay? So that would be, you would describe this as an antipolar mode, probably, right? And the key thing to notice here is that you can say that this antipolar mode, again, I insist heavily, transforms like this representation. So from the point of view of symmetry, there's no way that you can confuse it with any other. And that allows also to distinguish with this other antipolar mode. So you see this one, it's very different in characters because now the two LEDs here, they are going against each other, so it's really a different one. It transformed differently. That's two different kinds of antipolar modes, both at the endpoint, and that you can distinguish using this EREP notation. Okay. So this was for phonon modes here, but in fact you don't care very much whether this is a static distortion or whether this is a phonon, right? It doesn't matter from the point of view of symmetry. If it's a phonon, you just multiply this by some exponential I omega t or something. If it's a static distortion, it just describes the static structure as it is. So the point here is that there's been a considerable amount of work already to investigate all those possible combinations and distortions, so this is what I want to go into now. So if I want to step back a bit on the perovskites and forget about barium titanate, but be a bit more general, it's quite common to think of the perovskite as a distorted structure, first thing, and to consider elementary distortions. So in barium titanate, we've been discussing cation displacements, that's the polar instability. Okay, octahedral tilts, this is also very common. We've seen several examples, I think, since the beginning. And also you would have octahedral deformation. Michel mentioned Jantella. Deformation is in his lecture as well. So all those are kind of elementary distortion from the point of view of, say, the physical mechanisms that they involve, because usually they have different origins. And also they can be separated nicely using this symmetry classification. So this is a job that I would say, again, has been done. So it's all about finding your way into it. So in particular, those guys, Howard and Stokes, they did plenty of papers on that topic. So I pick up one here, but there would be many others. So it's a very long paper where you will find in particular this kind of table. And they will tell you, for example, that this Jantella distortion that they are considering in this potassium copper fluoride that happens to be the model for Jantella transforms like Ar4+. But then if you have a B cation displacements that's ferroelectric, gamma 4-, we have seen that one already. If you want an anti-ferroelectric or antipolar distortion, M3-, and so on and so on. So you can really classify all this and analyze them on the basis of this symmetry information. I will give you, I think, one last example of that. Is it okay with the time? Because I was super clever with the timer. Yeah, I think it's fine. So let me give you an example of how that can be used in a real case. So this is just from a collaboration we did some time ago, and this is about terbium, the solid solution between terbium manganite and terbium ferrite. Okay, so they are both perovskites. They share the same structure, this orthorhombic PNMA, like everyone. Okay. But there's one major difference, that this Mn3+ that you have in the manganite side is Jantella active, so you expect some octahedral distortion, okay, from it. And this one is Jantella inactive. So you expect some kind of change to occur, okay, even though the solid solution remains orthorhombic PNMA all the way. And you want to analyze that. So what you do is that you prepare your sample and you make some kind of structural refinements and you get all the atomic positions. Okay? So the question now is, how do you analyze all those atomic positions in the best possible way? And here there happens to be this thing that directly gives you a decomposition of the structure onto symmetry-adapted coordinates of the kind that I was mentioning. Okay? So in practice, this is what it would look like. So the pictures are maybe not the best, okay, but you will find this R4 plus that corresponds to the tilting. You will find this, where is it? You have this other tilting, the M3 plus. You see this time it's an in-phase tilting. You have this Jantella, this M2 plus, that's really a deformation of the octahedron, and then you have some secondary modes. So instead of just plotting some kind of atomic coordinates, you directly plot them into this special coordinate system. And you get these kind of things for the whole composition range. So this is pure terbium manganite, and this is pure terbium ferrite. And you see how they change with the respective weight also in the structure. So that would be the tilts here, R4 plus, which is the dominant, I mean the two tilts, 4 plus, 3 plus. Then you have this X5 plus, which corresponds to the antipolar motion of the terbium in the structure. That also contributes a lot. And what's always funny is to check this mode that corresponds to the Jantella distortion. Okay, well, you see that instead of interpolating linearly, it has this kind of funny behavior where it goes down and then there is a kink at roughly 50%. Okay, so this is how the average structure seen from XRD sees the evolution of the Jantella distortion in this particular system. And because we are using this symmetry-adapted basis, it shows much more easily than it would if you would, plot, I don't know what oxygen coordinates. Okay. So this is just as an example, and also an example of the use for this program Amplimode it's been around for some time now, but this is really the kind of tool that experimentalists are increasingly using as well. Okay, I think I will in fact finish on that. I had another example, but I will skip it. So I would just say what's next. So here I try to focus on atomic displacements, right? So there's many other topics that we could have covered. I mean, there's one selection rules in spectroscopy. There's all the splitting of orbitals and energy levels in a crystal field, so things that have been mentioned also earlier this week. This completely fits into this theory. You have all the symmetries of coupling phenomena, so in principle, this also plays a big role here. You have the analysis of domain structures and symmetries of domain wall and so on. So there's really a lot more topic that make use of all this formalism. All right, just one slide as a teaser for the next lecture on Saturday of just the kind of final result that you might expect for spectroscopy. So if we want to investigate the spectroscopic signature of the ferroelectric transition lead titanate, for example, you can again use the ERAPs, use those group-subgroup relations that you have, and see what they change. So here, this is again from the Bilbao crystallographic server, and they are very nice to you because they have a color code to show immediately what happens. If you remember, in barium titanate or lead titanate, I had 3 modes with this symmetry and 1 mode with this symmetry, okay? This one is the polar mode, so you see it in infrared spectroscopy, but you don't see it in Raman spectroscopy at all, and this one is completely silent, so you don't see it by any of those 2 techniques, okay? And now when you go to the ferroelectric phase, this mode splits into 2 different modes with different symmetries, and they are both active in Raman and infrared. And this one splits into 2 modes. One of them is active in both, and one of them is active in Raman only. Okay? So this immediately tells you what happens, how many modes you expect when you cross the transition, and so on. So this is to be continued on Saturday. Thank you very much for your attention for this tedious topic, and let's have a discussion.